Alright guys, welcome back. We just left off in the previous video in my photoelectric effect part 1 video. Right here is the exact place we left off, and we were just about to calculate the energy of the photon. Alright, because we found the work function, which is right here, and now we just have to find the energy of the photon. Alright, so let's write this a little bigger. Energy of the photon is equal to the Planck's constant times the speed of light over the wavelength. Okay, cool. So now let's go ahead and calculate it. Okay, so the energy of the photon, so let me go and write that down. This is the energy of the photon, or our light, or our light, right? Which is the same thing as a photon. So it's the energy of our photon is equal to the, let's go and write right here. So the energy of the photon is equal to the Planck's constant, which is 6.626. And also, guys, we wrote it right here just to remind us. So it's equal to 6.626 times 10 to the negative 34th meters squared times kilograms over seconds. Okay, so it's going to be our meters squared times kilograms over seconds. All right, so now that we have that, the next part of our equation is going to be the speed of light over wavelength. So the speed of light, go ahead and write this in a different color, is about 3 times 10 to the 8th meters per second over, and then let's write this in a different color. Let's go and write this in, let's see, blue. Yeah, blue's a good color. 3 times 10 to the 8th meters per second over the wavelength of the photon. All right, in the problem, and we saw that the photon's wavelength is 600 nanometers. But remember, we have to be very careful. We discussed this in the last video where we left off, that we can't just put 600 nanometers in the wavelength value right here that we're about to write down in here. We have to put the meters value because wavelength is in meters in the terms, and if we're talking about the energy of the photon equation. All right, so we're going to say divided by the wavelength, which is 600 times 10 to the negative 9th meters. All right, so that's the wavelength. Now, all together, we had to do a lot of work here. I mean, not a lot. We just have to pretty much multiply the numbers and then work out the units, okay, so that it can be in joules, which is what energy of photon is in. All right, so let's go ahead and do that. All right, so first, I would say let's work out the units. So that let's get the messy part out of the way. All right, so let's do this first. So we're going to multiply meters. Oh, let's do it right here. Meters squared times kilograms, right? Guys, that's the units for our Planck's constant. And we said, oh, that's not good. And we said divided by, nope, it's still not erased. All right, divided by seconds. And then we're going to multiply that by the speed of light, okay? So meters per second. Since we're saying seconds on the left side, let's just be consistent and say seconds. All right, so it looks even. All right, so right here, what we can do is that we're going to square the seconds on the denominator, and then we're just going to multiply the meters on the numerator. All right, so it's going to equal meters cubed times kilograms divided by seconds squared. I'll just write S for short now. All right, so that happened when we multiplied these two units together. Remember, we're not multiplying numbers right now. We're getting the units out of the way. All right, so now all we have left is we have to divide this whole thing by by meters, okay? And what's that going to give us? Let's go ahead and see, okay? So we're going to have meters. Actually, let's go ahead and do green. Yeah, there you go. Meters cubed times kilograms over seconds squared. And then we're just going to divide by meters, okay? So divided by meters, and technically we can write divided by meters over 1. And whenever you divide like this, we know that we can flip the denominator when we bring it up to the top, all right? So what I mean by that is this. So we're going to have meters cubed times kilograms over seconds squared, and then we're going to bring it to the top and multiply 1 over meters. So it's the reciprocal, okay, of meters over 1. And if we do this, we're going to get, let's combine these two together so we can see it more clearly. We get meters cubed times kilograms divided by seconds squared times meters. And here we have an exponent 1 here and a 3 here. So we're just going to subtract, or we can just cross it off from the numerator and denominator since it's a common. All right, so we're going to squeeze it in here somehow. Meters squared over seconds squared times kilograms. All right, so that's what we end up for our units. And hopefully that's familiar to you guys. That is equal to joules. Meters squared over seconds squared times kilograms is equal to joules. And that's why the energy of the photon's units is equal to joules. Okay, so that's the messy part, all right? We got the units out of the way. All we have to do now is just calculate the numbers by just multiplying it, okay? So let's go ahead and do that. All right, so 6.626 times 10 to the negative 34th, right? Let's not worry about the units because we just did. We just solved it all out and found that meters squared over seconds squared times kilograms is joules. So 6.626 times 10 to the negative 34th times 3 times, let's go ahead and make this not look ugly, okay? Times 3 times, all right, never mind, it still looks ugly, but still, all right, 3 times 10 to the 8th. Okay, I can't write today for some reason. 3 times 10 to the 8th. All right, so let's go ahead and calculate that first. And if you go ahead and calculate that out, you're going to get about 1.98. All right, let's do red, I guess. 1.9878. All right, 78 times 10 to the negative 25th. All right, sweet. So we're just one step closer to determining the energy of the photon. All right, so we just multiplied the Planck's constant value times the speed of light, and we got this value right here, 1.99 about, times 10 to the negative 25th. And now we have to divide this value right here by 600 times 10 to the negative 9th. All right, so let's go ahead and do that. So now we're going to divide this by our wavelength of the photon, which is 600 times 10 to the negative 9th meters, right? But remember, we just took care of units, right? So once you do this, you're going to get a value of about 3.313 times 10 to the negative 19th. All right, so that right there is your energy of the photon in joules. All right, so, and remember we just solved all those units, and we got meters squared over seconds squared, which we got right here, times kilograms, and we said that's also equal to joules. Okay, so this again, let's go and label this, is our energy of photon. Finally, right, we solved the energy of the photon. Now let's first, and what was the question, right? So let's go and scroll up and see the question. So the question is, what's the kinetic energy of the electron in the core of the rubidium metal? Well, remember the equation is kinetic energy is equal to energy of photon minus the work function. Well, we just found the work function in the previous video, right? Which is right here, and we just found the energy of the photon. So now let's go ahead and first, before we solve this, let's go ahead and think about what's happening. All right. So let's go ahead and look at the value of the energy of the photon. So we see 3.313 times 10 to the negative 19 joules. All right. And what's the value of the work function? 3.376 times 10 to the negative 19th joules. So which is bigger, right? The work function is bigger by a little bit, all right, but it's still bigger, right? 3.376 times 10 to the negative 19 joules is bigger than 3.313 times 10 to the negative 19 joules. So what does that mean? That the energy of the photon is not strong enough. It doesn't have as much energy, right, to overcome the work function of the metal. What does that mean? That the electron that's in the core, when the photon collides with that electron or that metal, in this case rubidium, that electron will not become a photoelectron, which means it will not get freed to the surface because the work function is greater than the energy of the photon. Okay, so right then and there, when the question says what is the kinetic energy of the electron in the core of the rubidium metal, right here, we can say that the kinetic energy will be, the solution is not going to be real because it's going to end up being a negative kinetic energy. And that's not possible, right? Because that we just said the energy of the photon right here in the equation is less than the work function of the metal. So we will not have a photoelectron. No electrons will be freed because that photon is not strong enough, sadly, okay? So that's what's going to happen. So we don't even have to solve this kinetic energy problem. So pretty much the solution of this is going to be that the energy of the photon, just go and write it out. The energy of the photon is not strong enough, right? In this case, we mean does not have enough energy to overcome the work function, of rubidium. All right. So there will be no photoelectron because a photoelectron means if that electron in the core gets freed via a photon, but the photon is not strong enough, so we will not have a freed electron. So let's just go and write that down. So no photoelectron produced. All right? Because the energy of the photon was not strong enough. It wasn't high enough. It couldn't overcome the work function. Just like we said in the previous video, we couldn't win the arm wrestle, right? We tried, we put in the energy, in this case, the energy of the photon, but the other guy was too strong, right? Which is in this case, we can say the work function. And so we couldn't beat them, right? Just like that, the energy of the photon could not overcome the work function and it could not free an electron from the core of the metal rubidium. All right, so let's look at an example that involves a photoelectron, all right, an electron that's actually freed. All right, so let me go ahead and pull up an example of that. And here we are. Okay, so we have the same alkali metal, right? You know what, let me go ahead and lock this real quick so it doesn't move. That way it can be more neat. All right, there you go. So we have our rubidium as our alkali metal still, right? And we said that the work function is 2.11 electron volts like the last problem. Okay, but this time the wavelength of the photon that will hit that rubidium metal and affect the core electrons is 580 nanometers. Okay, so remember previously it was 600 nanometers, now it's less. So one thing we have to mention before starting is that as wavelength decreases, all right, so as wavelength decreases, the frequency, guys, increases. Okay, so the frequency goes up. And what does that mean? If the frequency goes up, the energy of the photon increases. And we know that because the energy of the photon, right? So I'll say E of P is equal to Planck's constant times frequency. Just now we said if frequency increases, we see that the energy of the photon will also increase. Okay, and vice versa. All right, so now that we know that, remember we covered the units, the calculations of the units in the previous problem, that we found that joules is equal to, right here, meters squared over second squared times kilograms, so we don't have to worry about that. So, and plus we already know what to do, what the calculations are, so we can go through it much quicker this time and save time. Okay, so again, let's write the equation down real quick. Kinetic energy is equal to the energy of the photon, all right, minus the work function, actually, let me go ahead and write that in a different color, minus the work function of the metal, all right? So of the metal. All right, and if I'm being specific here, let's be specific here and say this is the kinetic energy of the electron. All right, if there is kinetic energy of the electron, that means we have a photoelectron, right? Because if we have kinetic energy, then that means the electron has some velocity, and if it has some velocity, which it means that electron is freed. Okay, because all right, if I keep on talking, we're not gonna finish. Okay, so let's calculate the kinetic energy. Okay, so first let's calculate the work function. Actually, we don't have to calculate it. We can just go ahead and look what the work function was in the previous problem, because we already calculated it in the previous problem, so we can save time there, guys. Okay, so right here is the work function, 3.376 times 10 to the negative 19th joules. All right, so 3.376 times 10 to the negative 19th joules is our work function of the metal. Okay, so work function of the metal, our rubidium metal, alkali metal. Okay, and now let's go ahead and calculate the energy of the photon. All right, so remember, energy of the photon is equal to Planck's constant times f, our frequency, and we said that speed of light is equal to wavelength times frequency, and we said we have to solve for frequency because we're given the wavelength. So if we solve for frequency, we're going to get frequency equals speed of light over wavelength, and then all we have to do, guys, is just feed this into here, into the frequency value, so that we'll have energy is equal to h times, let's write this a different color, times speed of light over wavelength. And now we can calculate the energy of the photon because we have all the values. Okay, so let's go and do that. So let's go ahead and bring this over here and do it here, so we have more space. Okay, so energy of photon is equal to the Planck's constant, which is 6.626 times 10 to the negative 34th. And again, we're not worrying about units because we already did the hard part for that, and we solved it and got joules. All right, so 6.626 times 10 to the negative 34th is Planck's constant. All right, and we multiply that by the speed of light, which is 3 times 10 to the 8th meters per second, over our wavelength. Again, let's be careful. We have to write the wavelength in meters. So we have 580 nanometers, but we know that 1 meter has 1 billion nanometers, so it's going to be 580 times 10 to the negative 9th meters. And then if you go and multiply all that out, you're going to get energy of the photon is equal to about 3.427 times 10 to the negative 19th and joules. All right. Okay, so we found the energy of the photon, and we found the work function in the previous problem. And right here, guys, you can automatically see that the energy of the photon is greater than the work function. And what does that mean? That we won the arm wrestle, right? We put more energy into our arm muscles, right, to beat the other guy. Okay, so we beat the other guy's work function. He couldn't handle our strength, so he lost and we won. Just like that, the energy of the photon won the battle with the work function and overcame the work function, and we can see that because the energy of the photon is greater than the work function. And so our photon will strike that core electron, and that core electron will be freed, becoming a photoelectron, okay, on the surface of our rubidium metal. It will go to the surface of our rubidium metal. All right, photoelectron is achieved. All right, sweet. So now that we know the energy of the photon and the work function, we can just literally subtract the two and find the kinetic energy of the electron, because we know it has kinetic energy because it was just freed from the core to the surface. So it moved, which means it had velocity, which means it had kinetic energy, because it also has mass. An electron has mass. Okay, so let's go and calculate the kinetic energy. And that will be our answer for number 1. Okay, so the kinetic energy of electron is equal to, let's go ahead and see that. So we have the energy of the photon right here minus the work function. Okay, so the energy of the photon we just calculated was 3.427 times 10 to the negative 19th, right? Both of them are in joules, so we don't have to worry about that, minus what? The work function, okay? And the work function is 3.376 times 10 to the negative 19th, again, joules. Okay, and now all we have to do is just subtract that. So we're going to get, let's just say it right here straight up, all right? We're going to get a kinetic energy of, or we're going to get the value of the kinetic energy of the electron in joules, and that value is going to be around 5.124 times, it's going to be really small, 10 to the negative 21st. All right, and remember, this is kinetic energy, so we're going to have joules. All right, finally, right? This is our kinetic energy of our photoelectron, right? This isn't, we have to be specific. This is a kinetic energy of, so we're just going to draw an arrow and say, in particular, our photoelectron, because our electron was freed by a photon, all right? So now we solved number one, so this is the answer to number one, all right? What does number two say? Number two says, what is the velocity? What's the velocity of the photoelectron? We found the kinetic energy, but what's the velocity? All we have to do here is just go a step further, okay? What's kinetic energy equal to? Right? What is kinetic energy? Kinetic energy is 1/2 times the mass times the velocity squared. All right? And we know the kinetic energy because we just solved for that, and we got 5.124 times 10 to the negative 21st joules. All we need is to find the mass, but we don't have to find the mass because we're talking about the kinetic energy of that photoelectron, right? Of photoelectron, which is an electron that's being freed. Well, what's the mass of an electron, right? The mass of an electron, so let me go and write that down. Mass of electron is about 9.11 times 10 to the negative 31st kilograms. All right, sweet. So as you guys can see, we have all the values to solve for velocity, right? So all we have to do is just think a step further and think of the equation as a whole of kinetic energy. Okay, so let's solve and be finally done. All right, so let's do this in, let's do this in gray, I guess. Okay, so the kinetic energy, 5.124 times 10 to the negative 21st joules, right, is equal to 1/2 times the mass of an electron, of the electron, which is 9.11 times 10 to the negative 31st kilograms, times velocity squared. All right, so now this is just a simple algebraic equation, right? So let's just divide by 0.5 on both sides to get rid of the 1/2. Okay, so it's going to be 5.124 divided by 0.5, right? So it's going to be 5.124 divided by, or let's write this first, 5.124 times 10 to the negative 21st joules, right? Divided by 0.5, or 1/2, right? Equals 9.11 times 10 to the negative 31st kilograms times velocity squared. Okay, now we just have to divide 9.11 times 10 to the negative 31st kilograms from both sides to get velocity squared by its own. That's going to get us about 1.125, all right, times 10 to the 10th equals velocity squared, right? So I just did everything at once. So I divided this value right here, and then I took that value and divided it by this value, okay? Because you have to move this value to this side, right? Okay, and we have to divide, right? We're dividing 9.11 times 10 to the negative 31st kilograms on both sides. Okay, so now we're ended up with this right here, and now all we have to do is just square root both sides. So V equals, our velocity of that photoelectron equals the square root of 1.125 times 10 to the 10th Let's go and write the answer up right here. So the velocity of the photoelectron is equal to about 1. Oh, this is a large number, all right? Let me just shoot, I wrote in the wrong place. Is equal to 10606.356. All right. Oops, where's my decimal? There you go. So that's a huge number, right? 106,063.56 meters per second. All right, let's not forget that. Meters per second. All right, so that's our answer to number 2, guys. Right, that's the velocity of the photoelectron that was freed because the energy of the photon was greater than the work function of the metal. Okay, so that was photoelectric effect part 2 for you guys. All right, and hopefully you guys watched photoelectric part 1 or photoelectric effect part 1 in my previous video, and hopefully now it makes much more sense. Okay, so that was a lot of calculations, but that's the basic idea of the photoelectric effect, where a photon knocks off an electron from the core of a metal, right? In this case, rubidium, which is an alkali metal, right? That electron gets freed because the energy of the photon overcame the work function of rubidium, the metal, and that because the energy of the photon overcame the work function of the metal, we saw an electron being freed, and when the electron was freed, it was called a photoelectron because it was freed by a photon, right? And when that electron was freed from the core to the surface of that rubidium metal, we knew that it had velocity, right? And we know that an electron has mass, so we knew that it had kinetic energy. And to solve for the velocity, right, all we had to do was set the kinetic energy to its equation, which is 1/2 mv squared, and we solved for v, and we got 106,063.56 meters per second, which is the velocity of the photoelectron when it was freed to the surface of the metal. All right, so that was it, guys, and I don't know why this is here, but let's go to another page, and hopefully I'll see you guys in my future videos where I'll talk about more cool topics in chemistry, like electron configurations and quantum numbers, and more cool topics, and also topics in bio and biochem and physics. All right, and don't forget to hit that notification bell so you know when I'm publishing my videos, and don't forget to subscribe and like. All right, and see you guys next time.